The auditory system, part 2, organ of Corti. This important part of the inner ear. Scala vestibular 2 is there's a scala vestibular, there's a scala media and scala tympani. There's a so-called Reisner membrane between vestibular and media, and we have a tectorial membrane, as I talked about. We have a basilar membrane. It should be between scala media and scala tympani, and we have inner hair cells and we had outer hair cells, and we have some auditory nerve connections. Afferent is from the hair cells to the brain, and efferent is from the brain back to the hair cells. And there are some liquid in scala media is indolent. It's called high potassium concentration of potassium ions, and we have in the so-called perilimbs high natrium ions concentration in the tympani. Okay. Function of the inner hair cells. Inner hair cells, they transform mechanical vibrations into electrical nerve systems. Okay. They transform mechanical vibration into electrical nerve system. How does it work? Functions of inner hair cells. Yes, you have the inner hair cells with the stereocilia, and in this inner hair cell there are some so-called neurotransmitter, signal stuff, you can say. And when the stereocilia is bent to the right, then the hair cell is depolarized. That means that some of those potassium ions coming to the hair cell, and then that means that the neurotransmitter is released, and when the stereocilia is bent to the right, and that means that some activity in the nerve fibers is going on in the form of spikes. Some electro potential is going on by those neurotransmitters. So the nerve, the spikes and the activity in the nerve fibers brings those electric signals to the brain in a very complicated way. Okay, the basilar membrane displacement towards scala media. Stereocilia bent to the right, and then this transmitter is released. Tip links open ion channels, potassium ions enter cells, depolarization of cell about minus 45 millivolts, release of neurotransmitter, spikes generated in the auditory system. Okay, and it's a transducer from mechanical to electrical signals. When the inner hairs, when the stereocilia are upright up into the left, there is no activity in the nerve connection to the nerve fibers. Also nerve fibers. Function of the inner hair cells. They transform mechanical to intracellular potentials. With low frequencies, it means fine structure. With high frequencies, it means envelope. You can say high frequencies. No, a simple hair cell model. It's you can speak about it as a half wave rectification plus low pass filtering. A center frequency about 1 kilohertz. Yes. It's high frequencies means envelope structure. You can say envelope oscillations instead of fine structure modulations. Low frequency fine structure, high frequency envelope. Okay. A way to remember to speak about it. So what is the purpose of the outer hair cells? Outer hair cells amplify basilar membrane motion. Outer hair cells realize a cochlear amplifier. Okay, there's some active region and the displacement of the base is enhancing. Yeah. Yes. So, yes. Okay. Basilar membrane movement. Tuning curve. What is a tuning curve? It measure basilar membrane displacement at a fixed location in response to tones with varying frequency and level. If you have a graph with frequency, first axis, and basilar membrane movement at second axis, you can see that at higher, when the decibel, the pressure is growing, yeah, they have this form that's about a maximum at some places, at some frequencies, but this maximum frequency is going to be less when the dBs are increased a little bit. There's a so-called spread of frequencies to the left, to the lower side. Yeah. Yes. Yeah. And for the higher side, there's a slope very fast. Yeah. You can say tuning curves a little say is kind of another opposite kind of excitation pattern. Tuning curves measure response to many sinusoids at a fixed location. Fixed location. What is excitation patterns? It measure responses across places with different center frequencies with one sound, not a fixed place, but one sound. Yeah, then we get an excitation pattern. It can be explained. The curve excitation curve can be explained at a certain frequency. Sound frequency can be explained by the auditory filters. Hair cells to auditory nerve connections. Of those 30,000 afferent fibers, 95 are connected to the inner hair cells and 5 to the outer hair cells. Of 1,400 efferent fibers from brain to back to the hair cells, 60% are then indirectly connected to inner hair cells, and 40% are directly connected to the outer hair cells. Yeah. Inner hair cells are the main transducers of information to the higher stages of the auditory system, as I talked about. Mechanical to electropotential. Outer hair cell modulate responses. We have some action potentials in a single neuron. Maximum spike rate in a single fiber is limited. I think it's no more what's it called, frequency about 200 hertz. About that, I can't remember exactly. But timing of spikes, interspike intervals provide information. So together, many spikes can can increase the frequency range. So period histograms of one auditory nerve fiber activated by 1100 hertz shown. Yeah. 40, 50, 60 dBs. And yeah, 90. Spikes are evoked in only one half of a circle of the waveform. This is called phase logging, only when the stereosilius are bent to the right. Input level is coded by spike rates. Input level is coded by spike rates, but with limited dynamic range. Yeah. Action potentials in auditory nerve. Combining many fibers allowed 5 logging up to about 5 kilohertz, 5000 hertz. Combining many fibers can give a phase logging up to about 5000 hertz. Yeah. You have a waveform, a pressure, and then auditory nerve spikes with interspike intervals. Yes, and the combination of many fibers, single fiber and many fibers. Action potentials in the auditory nerve. There are some spontaneous firing with no sound input. And this is divided in high spontaneous rate fibers and low spontaneous rate fibers. There's a firing rate up to about 200 spikes per second. That's it. With high spontaneous rate fibers, from a level about 20 to 40 dBs, the spike rate, firing rate will increase from about 50 up to the maximum about 200 per second, spikes per second. And when the low spontaneous rate fibers are more slow increase, starts to increase about 40, with almost 0 dBs, and increasing up to maximum about this threshold range, this pain threshold, more than 100 dBs. So high spontaneous are fast growing, and then it get constant. The firing rate gets constant. Slowing low spontaneous rate fibers have the firing rates in spikes per second are slowing, growing. Large dynamic range and high sensitivity is achieved by combining many fibers. Large dynamic range and high sensitivity is achieved by combining many nerve fibers with different properties, high or low spontaneous rate fibers. We have again those neural tuning curves, similar tuning as mechanical on the basal membrane. Yeah, so you can just turn it the other way. Tuning curves, a frequency response of single auditory nerves at a single place. Input many sinusoids at different frequencies. The minimum sound level needed to elicit threshold activity. Yeah. So it's the other way, you can say. Yeah. Whoop. Hips. Yes. And sharp tuning. It's sharp tuning shallower on the low frequency side. Same as I talked about before. That's it. That was part 2. Thank you.